Applying linear regression. Printing the main squared error. Using the OLS regression results, we got a lot of the information in the model summary output. Let's understand the key things that we've inferred from this output. 1. TV and radio have significant p-values, whereas newspaper does not. Thus, we reject the null hypothesis for TV and radio. There is no association between these features and sales. However, we fail to reject the null hypothesis for the variable newspaper. 2. TV and radio ad spending are both positively associated with sales, whereas newspaper ad spending is slightly negatively associated with sales. However, this is irrelevant since we have failed to reject the null hypothesis for the variable newspaper. 3. This model has a higher R-squared value, 0.897, than the previous model, which means that this model provides a better fit to the data than a model that only includes the TV variable. Feature selection. How do we know what features need to be included in a linear model? Here's some ideas. 1. Try out different models and only keep the predictors in the model if they have small p-values. 2. Check whether the R-squared value goes up when you add new predictors. Let's try this. im.r². Observing the output, we get similar R-squared values. R-squared will always increase as you add more features to the model, even if they are unrelated to the response. Thus, selecting the model with the highest R-squared is not a reliable approach for choosing the best linear model. Handling categorical predictors with 2 categories. Up until now, all the predictors have been numeric. What if one of the predictors was categorical? Let's create a new feature called size and randomly assign observations to be small or large. Importing NumPy. Import NumPy as NP. Setting up a random seed. Assigning observations as small and large. Creating a dummy variable that represents the categories as a binary value. Let's redo the multiple linear regression and include the IS large predictor. Now you may ask, how do we interpret this IS large coefficient? For a given amount of TV, radio, newspaper ad spending, being a large market is associated with an average increase in sales of 52.42 widgets as compared to a small market. Let's create a new feature called area and randomly assign observations to be rural, suburban, or urban. Now we create another dummy variable. Here is how we interpret the coding. Rural is coded as area underscore suburban equals 0 and area underscore urban equals 0. Suburban is coded as area underscore suburban equals 1 and area underscore urban equals 0. Urban is coded as area underscore suburban equals 0 and area underscore urban equals 1. Let's include the two dummy variables in the model. How do we interpret the coefficients? Considering all the other variables as fixed, being a suburban area is associated with an average decrease in sales of 106.56 widgets, as compared to the baseline level, which is rural. Being an urban area is associated with an average increase of sales of 268.13 widgets, as compared to rural. Great, now we know how to explore and examine the advertising data. Let's quickly recap the steps we've covered so far. 1. Visualize the relationship among the features and the target variable. 2. Apply linear and multiple linear regression. 3. Hypothesis testing. 4. Feature selection. 5. Handling categorical predictors. In prediction. Let's now look at the challenges that can occur in prediction. If your model is not appropriate, it may have underfitting or overfitting issue. Underfitting in your machine learning algorithm occurs when it cannot capture the underlying trend of the data. It disturbs the accuracy of your machine learning model. In this situation, the algorithm will not work well on test data, and retraining may be needed to find a better fit. Overfitting occurs when you train it with a lot of data. It does not allow your model to categorize the data correctly because of too many details or noise in the data. In this case, the accuracy for training data of your model may be good, but the model does not generalize well to the overall population. In this situation, the algorithm will not be able to give good predictors for new data. So what is the solution for overfitting? Regularization solves overfitting to the training data by restricting the value of parameters that are estimated in the model. Look at the given graph. Here, the red line indicates the parameter selection for training data, and the red dots represent the training data. Similarly, the green line indicates the parameter selection for test data, and the green dots represent test data. The loss function includes two elements. The first is the sum of square distances between predicted and actual value, and the second element is the regularization term. Regularization does not improve the performance of the algorithm on the data set that has been defined as model parameters. However, it can improve the generalization performance, that is, the performance on new unseen data.